So now we're going to look at how we can clean up some of those aberrant or misclassified pixels that we find in the Rapid Eye classified version. And if you look here, for example, this is comparing the same locations in the Landsat 2001 image, the classified version, and the Rapid Eye classified version. And we can see both a difference in the cell size as well as the level of detail of features that we find as forest and non-forest in the two. Now, obviously some of this will be due to changes in forest to non-forest or non-forest to forest. But generally, if you look at features that have no effect on becoming forest, like a linear feature such as this road, you can see it has much more detail over here. Now, because of that injection of fine-scale detail, we end up with a lot of these aberrant pixels. So we can clean those out by using what's called a majority filter. So we can filter out based on majority. Returning back to ArcGIS here. Here I have my ML class RE21 and my ML class L721. And I've renamed them here to be consistent with what is in the exercise. So here in the maximum likelihood classifier for the Rapid Eye, we have these issues of a whole bunch of often small abhorrent pixels, where these single ones, and maybe groups of two, likely just represent misclassified pixels. So I'm going to go over to geoprocessing, and I'm going to type majority filter. And you'll see that under generalization in spatial analyst tools. So majority filter. Now, since I'm going towards my final analysis, I'll open up majority filter. I'm just going to go back over here to analysis environments, and I'm going to set those key raster environment analysis tools. So we want this thing to eventually match up with our ML class L7, the Landsat classified image. So for extent, I'm going to have the same extent as ML class L721. Snap raster will also be ML class L721. The mask will be L721 as well. And the cell size will not touch right now. Not for this particular stage. So I'll just click OK. So my input raster, I'll just drag over my ML class RE21. The output raster I'm going to call ML class RE21 filtered. Number of neighbors to use, 4. And replacement threshold majority. I think I'll choose that 8 instead. And then the replacement method, half. So that gives a little more leeway in terms of we want at least half of the area to be majority of one class or the other before changing the pixel. And if it so happens that there's equal halves, it will put a no data into that cell. So now I can click Run. And we'll just be on this here in a second. Now I'll go back and again change to my same color scheme so we can look at a quick comparison. So I'll right click here and I'll make that green. Remember, pixel value 1 or class 1 is green. We want the darker green. Well, it doesn't still look quite right, does it? I think it's the green right there. That's better. And then for non-forest, that kind of darker red here, like that. So I'll just turn off the filtered one, and you can see how they've disappeared. Many of those aberrant pixels have disappeared. And also at the same time, some of the areas that we might consider as features, like this down in the bottom right here, right there, those have become more compact as well. But all those small misclassified pixels are gone. Some you may choose to run that more than once if you want, twice, and it will get rid of even more of the small individual pixels that might be left over. So now I'll turn off my original ML class RE21, and the next step is going to be to bring the ML class RE21 filtered to the same cell size as ML class L721, which is the Landsat 7 classified image. And you can see they're quite different here. Landsat has a 30-meter cell size in its multispectral bands, whereas the RapidEye has a 5-meter cell size. And so the amount of detail you can see, particularly spatial detail along edges, is very different between the two. But to do a quantitative comparison of these two maps together, we need to be able to have them both at the same cell size. So here we have, again, back in the laboratory exercise examples, we have a 30-meter resolution and a 5-meter resolution. And so any subsequent analysis is generally going to be done at the 30-meter resolution. So as a general working rule, the analyses that you undertake are almost always going to be done based on the raster layer with the coarsest resolution, since that is the spatial size, or the spatial the greatest amount of spatial detail you can go into, because you can't get a 5-meter, you can't get more spatial detail out of something with less spatial detail. Actually, this kind of looks, if it looks a little bit like a face here, doesn't it? There's an eye, a mouth, and maybe some sort of weird nose there going on. So that's interesting, but has nothing to do with the exercise. Just a coincidence. So we need to go from 5-meter resolution for the ML class RE21 filtered layer, that's the majority filtered layer, to a 30-meter resolution. So going from what you see here in A to what you see here in B. Now to do this is a generalization step. And we have to do a neighborhood statistic in order to do this correctly, using a majority resampling technique. And conceptually it looks like this. So our 5 by 5 meter cells, right? There's how many 5 by 5 meter cells within a 30 by 30 meter cell? Well, you're going to have 6 by 6 equals 36. So there's 36 5-meter cells in a single 30-meter cell. And this is what's showing here, is the extent of a 30-meter cell, and then within that cell I'm showing the part of the existing RapidEye classified image, where we have forest and non-forest in there. This is not something that can be resolved in 30 meters. So in 30-meter cell, this is either forest or non-forest. Whereas with a 5-meter cell size within that 30 meters, we can see differences. But somehow now we have to generalize all these forest and non-forest cells to decide what this larger cell here will become. And if we use a majority rule, well, we see we have more green, so more forest than gray, which is non-forest. And so that new cell will become a forest cell. And so we lose information in this step. When we generalize, we lose detail and we lose information at the sub-pixel level. So the pixel level here is now 30 by 30, and we have no way to discern variation within that unit once we've undertaken that transformation to create a majority resampling of that space from 5 meters to 30 meters. So for this to be effective, we're going to go now and set our cell size in the environments first to the Landsat 7 layer at this point. So we didn't do it previously, see, because we were just filtering. Now we're going to change the cell size. And we'll do that resample at this point. So we'll just go and do that back in ArcGIS Pro. I'm just going to zoom out for this to a layer. So the layer I'm now working with is the ML class RE21 filter, not the ML class RE21, since that's the filtered one up here that I'm interested in, where we got rid of those misclassified pixels. So I'm going to click on Environments, go back down to Cell Size, and now choose, same as layer, ML class L721, the 30 meter resolution Landsat classified layer. And everything else can stay the same. Then I go to Geoprocessing. I'll click back here. I'll go to Resample, which is under Data Management Tools. So Resample, Data Management Tools, and under Raster Processing, Resample. So I click on Resample. My input raster is going to be my ML class RE21 filter. So I put it into the input raster here. My output raster is going to be called ML class RE21 classified. So I'm just going to copy that from here rather than type it out. Go back. And this will be the name of my output raster. Output cell size I don't have to touch because that's already set in the environments. But since it's an option here, I'll choose ML class L721. And that'll ensure that it will now say 30 by 30. And then the technique for resampling, we'll use nearest neighbor. Or what we really want to use is majority. So nearest neighbor resampling is the default. Majority is what we want, since we want each new cell of 30 by 30 meters to be taking on the information class, forest or non-forest, based on how much forest or non-forest there is within that 30 by 30 meter cell on the RapidEye 21 filtered layer. So, didn't change there. There we go, majority. So once we've done that, we just click Run. And I need to change my colors. So 1 again, we'll go to green. That's a green, yep. And 2, non-forest, to that darker red. So here I'm just turning on and off that's the 30 meter version, and that's the 5 meter version. If I zoom in, I'll see the coarseness that I've introduced through this generalization procedure. So if we look at just, for example, this cell here, right there, and I'll turn off the current 30 meter version, and we'll see that in that cell right there, there was a mixture of green and red, and that it ended up being mostly green. And you can also see how the geometry and detail of the edges of these features has changed substantially. So what here, for example, was clearly a northwest, all right, but it's about northwest south or northeast southwest orientation now just becomes a single cell at 30 meters, which has no orientation. So if we zoom back out to the layer, zoom to layer, I'll turn off my filtered one now since we won't be working with that anymore. And then we have a layer, and I'll bring up my ML class 21 so it's just underneath this one. So the ML class RE21 classified is the rapid eye, and then the ML class L721 is the Landsat. And we can look at areas. So for example, I can see here that if I just zoom in this area, I saw a big change by turning it on and off. So that's, right now we're seeing 2001, and now we're seeing 2016, 2001, 2016, 2001, 2016. So obviously here, there was, in this region, you can see the forest loss. The other way, of course, we can look at that, we could click on this and then the Appearance tab, and we could say swipe. Swipe it in different directions. So this swipes the one that's selected, that's the top one. So we can see this area here was forest to non-forest. Forested area to non-forest. So we see this area of forest loss between 2001 and 2016. So how can we then figure out how much forest has been lost or gained during that period of time for this entire region? So that's what we'll look at next. And that just requires a bit of map algebra. Before we actually go to comparing the two and using a bit of map algebra, we need to test the accuracy of our results, our classified results. So here, for example, we have classified results, and where the red dot is on the left-hand side, it falls within a green, which is forest, and on this, in this example here, non-forest is black. So the question is, well, this was classified as non-forest, this pixel that it fell on. So then we look at that same location in our multispectral image, and we see that, in fact, it is not forest there, rather than forest, where that pixel is. It's clearly in a clearing. And so in that case, that was a misclassified pixel. Now, obviously, that just shows one wrong or misclassified pixel. We need to find it at a number of locations. So we take a number of locations over here, over here, over here, over here, over here, over here, etc. And then at each of these locations, we'd see or we'd observe what's there. That's called the ground truth. So a ground truth observation. Likewise over here, non-forest. Over here, it's a tough one. Maybe I'll erase it and turn out. That looks like it might have been in forest. We'll say that's forest. That's probably still forest. That one is forest as well. And this one is non-forest. So here I have, that's a forest. I have 1, 2, 3, 4, 5, 6 ground truth points. Then I would see if they correspond to the same information classes on the image over here. I'd say, okay, this one over here is non-forest, so that one's wrong. This one over here is non-forest, and that one's wrong. This one over here is forest, and it's wrong. It's not forest there. This one says forest, and that's maybe around here. Let's say that one's right, and this one over here is forest, and that's right. So we look at it that way. We look at the image, the original remotely sensed image, and you can look at it in any type of band combination you want, and you decide and record where you look at it with a point, and record whether what you see there is forest or non-forest. And then, once we have those ground control points, we can have automatically the information classes extracted at those points, and we can create what's called a confusion matrix. And we do this by starting just with the create accuracy assessment points, in which we will then add our observations as the ground truths. So I'm going to go back to ArcGIS now. So back in ArcGIS, I'm just going to zoom back to the layer here. And we'll do the accuracy assessment on the ML class RE21 classified layer, just for this example. You would do it also on the L721 as part of the exercise. So with the RE21 classified, I'm going to go back to my geoprocessing tools, and I'll search for create accuracy points. And that's right up here under image analyst or spatial analyst. So create accuracy assessment points. So we have to input here our classified layer, because this is the layer which the points will be created randomly on, and for each point it will extract whether it's forest or non-forest, and then we can ground truth those. And then we say output accuracy assessment points. We'll call those just ground truth. So ground truth. The target field will be classified, and that just means that's the field that will be filled up with values from this raster for each random point. We're not going to go with 500 here. We're just going to go with 20 as an example. Generally, you would want to do a minimum of 100 of these. And the sampling strategy, we're going to use random. And we click Run. This is going to create a new feature class layer with points. So now we can see, and I'm just going to change the color of these to black so they're a bit easier to see. There we go. So now we can see the 20 random locations. So what I want to do now is ground truth those. So I need to open up the attribute table, and we'll see classified. So just as an example, classified 1. 1 means forest. So the first point, if I zoom to it, is within forest, and we can see that right there. There's the point, and it's within a forest. Turn off that swipe tool, go back here and turn on my Explorer tool. So that's in forest. I'll make that a little bit bigger as well, I think. Makes them easier to see when we're doing the ground truthing. Let me go to appearance here. And let's make it a bigger dark circle like that. There we go. Slightly larger circle is always useful to see. So now I need to bring back in the original RE Rapid Eye 21 layer. So I'll just go to my catalog, imagery, down at the bottom here, RE 2016-07-20. So now you'll see that I have ground truth as my first layer. My second layer is the remotely sensed image, the Rapid Eye. My third layer is the classified version of the remotely sensed image. So now I can see right here, I'll look at the first point again, turn those back on. That is, and I might want to zoom out a bit, I would say that is forest. So In the ground truth, I type the value 1 for the first point. Then I click on the second point, zoom to it, and I would say that is probably not forest. No. So that's a 2. Because remember, pixel value 2 is non-forest. Then I'll go to the third one, zoom to it. Definitely not forest. So that's a 2. Fourth one, zoom to it. That's definitely forest. So I put a 1 there. Fifth one, zoom to. I gotta zoom out a bit to tell there. That's a tough one. I would say that's probably not forest, so I'm going to put a 2 there. And it's very important when you're doing this that you don't let the classified value bias your decision. You should just ignore the classified one right now, and you concentrate on whether or not what you see is forest or non-forest. So on the 6th point, I'll zoom to that one. I would say that's not forest. 7, zoom to. That's a tough one, isn't it? Turn that off for a second. I would say that's forest. 8, zoom to, forest. 9, zoom to, not forest. 10, zoom to. It's a tough one. Probably not forest. Yeah, not forest. Uh, 11, zoom to, not forest. 12, zoom to. Yeah, that's not that is forest. Yeah, that's forest. It's a little bit more depth. It's right on the edge. I think that's forest. So, which one is that? 12? Yeah. Forest. 13. Zoom to. That's probably forest. It looks like forest by the color. But we'll just look at the context. Yeah. 14. Zoom to. Forest. 15, zoom to, not forest. Doesn't look like forest to me. No. You can see that's a field, obviously a agricultural field. Then there is a stream going through there. You can see the dark riparian vegetation around that stream. So it's a riparian zone. But at that GCP or ground control point is not forest. 16, we're almost getting there. Zoom to, not forest, definitely. Forests aren't white. Zoom to, that's forest. So 18, zoom to, I don't think that's forest. That's tough. That's a tough one, but I'd say that's not forest. It looks like probably somebody's backyard. And 19, zoom to, forest. So now we've filled all those in. We've ground truth. Oh, there's 20. I forgot that. Almost done. Zoom to, not forest. Enter. There we go. So now we have a completed ground truth table, and you want to click on the table view tab, and this is where you can do different things that you might want to do there. So you can look at the different options there. We're not going to touch any of them right now, and we're going to go over to the edit tab once you've had a look at the table tools, and click on the save button in the manage edits group. Save edits? Yes. So the next thing is click on the map tab. Make sure you clear any selections. Then we're going to go back to our geoprocessing tools, and we're going to type in here confusion. And we'll find the compute confusion matrix. This uses the correspondence between the classified value and the ground truth values to tell us how many things are correctly classified and how many things aren't, and gives us a kappa value. So I'll go there. There it is, compute confusion matrix. And it takes in our ground truth data. And then the output confusion matrix, which is a table. So I'll just go here. I'll go into my imagery geodatabase, and I think we call it something. And that name will be just confusion matrix. And I'll just click save. And then I just have to click run, and it'll put a standalone table into my contents pane. So I'll now open up that confusion matrix table and have a look at it. I'll just undock it here. So it tells us here in the first column, or the second column, forget the object ID column. We're interested in the second column here called class value, C1 and C2. C1 is pixel value 1, which is forest, and C2 is pixel value forest, non-forest. And then we'll see the same in two columns right beside class value, C1 and C2. And I've just accidentally sorted these. There we go. So C1 column and C2 column. So pixel value 1, forest, 2, non-forest. Then, if we look at the intersection, let's say, between column 1 and row 1, where the two C1s intersect, there's 9 there. So 9 out of a total of 10 in that row were correctly classified because they were both classified as a value 1 forest and ground truth as a value 1 forest. So that's 9 out of the total for that row, which is 10. And then it tells us that a C1, a forest, was classified as a non-forest in the second column here. So one instance of forest was classified as non-forest. So 1 out of 10 was incorrect. Then for C2, which is non-forest, we have 0 in the C1 column. And in the C2 column, we have 10. So 10 out of 10 were correctly classified as non-forest. And then looking over here, we have kappa, which is 0.9. So you can think of that as a very high kappa value, in that that would mean, in this case, that we have a fairly accurate classification. And that's what we want. The last thing we'll do is quantitatively compare our two predictions to see where we have either gained or lost forest in that 16-year period. So I'm going to turn off my ground truthing points right now, and I'm just going to turn off the ground truth. And what I'm interested in right now is just the ML class 21 zoom to layer here. The ML class RE21 classified, and the corresponding one from 15 years earlier from Landsat 7. And we'll just do a bit of map algebra. So I'll click on Analysis, Python. And in the Python window, I don't need, this is just old stuff that's in there. So I'll clear that. And I'm just going to make this a bit bigger. so it's easier to see, like so. And I'm just going to make the window a little bit smaller so it doesn't take up the entire screen. So the first thing I'll do is I'll just say from arcpy.sa import all. Then I'll make a new temporary raster called diff, and that will be equal to raster. And the first raster I'm going to put in is the ML class L721. So that's the 2001 maximum likelihood classification. And I'll subtract from that the ML class RE21 classified. So I'll just say raster and then choose that variable there. I'll have to make that a bit bigger now so you can actually see it. I don't think it needs to be all this big. I think you can see that fine, like so. And then I hit enter. So I'm subtracting from the 2001 image the classified 2016 image. So wherever it was 1 in 2001 and also 1 in 2016, 1 minus 1 is 0. So there's no change. Likewise, if it was non-forest, value 2 in 2001 and a value of 2 non-forest in 2016, 2 minus 2 is 0. So here in this diff layer, I'm going to close this, well, let's make it a bit smaller there. Just so you can see it. So in the diff layer here, 0 represents no change. So for no change, I'm going to make it no color. I'm going to turn off all my layers except for that one. So the change now is going to be -1 or 1. So what does -1 mean? -1 means that in 2001, the value must have been forest, 1. Because if you subtract from 1 the value 2, you get -1. So the value had to have been forest in 2001 and non-forest, a value of 2 in 2016. So I'll make that black to represent forest loss. And thus, the only other option then is if it's a value of 1. So if it was 1, that means it was non-forest in 2001, and that would be a value of 2, and forest in 2016. 2 minus 1 is 1. So that's forest gain. So I'll make that dark green. So here we can see then we have a map of forest gain and loss. Now you'll notice that most of the forest gain are linear type features along highways or roads and stuff like that. And so these probably aren't real forest gain, just differences in the spatial representability of roads at 30 meters in Landsat versus roads at 5 meters in the rapid eye image. What we're really interested in are contiguous zones of forest gain or loss. So a contiguous set, and I'll just go back to my map here, explore. Contiguous are large things like that. So remember, black means forest loss in the 15-year period. We have large contiguous zones of forest loss. very few large contiguous zones of forest gain. So most of the forest gain is just spurious pixels. But we do see consistent, large, contiguous regions of forest loss. And that tends to be what's important. And if we look at the diff attribute table, for example, and I sort it, or I look at it in terms of the classes, we can see that in terms of forest loss, we've had 9106 pixels. Far more forest gain, but again, most of that are single pixels that are just spurious because of the different resolutions of the sensors.